So in this video, we're going to look at a slightly more complicated example than we looked at in the previous video, and we're going to need to use the inverse tangent function to resolve this integral. So I'm going to start off by rewriting the integral. So I have the integral of 3 over 10 plus 8x squared dx. And even though it doesn't look like it, what we're going to identify is that we really have a 1 over the sum of squares form. So the arctangent function is going to be the tool to use to resolve this integral ultimately. So first step in this would be to factor out any constants that we can to kind of clean things up. So I see that I have a constant 3 in the numerator, so I'm going to factor a 3 out, which is going to leave a 1 in the numerator position. Here's my dx. But I also want to notice that in the denominator, 2 shows up as a common factor for both the 10 and the 8, so I can also factor a 2 off of the denominator using the distributive property, and that's going to leave behind a 5 plus 4x squared. And I really do have the sum of squares here in the denominator, even though maybe it doesn't look like it. What I want to remember is that a just has to be a positive real number, and it doesn't have to be a nice positive real number. There's no reason why it has to be, for example, a perfect square. So we want to recognize that 5 can be written as the square root of 5 squared. So this is still equal to 5, and if we wrote it like this, then our a would equal the square root of 5. So I'm going to rewrite the integral again as 3/2 times the integral of 1 over, and I'm going to write it as the square root of 5 quantity squared plus, and right here 4x squared can be rewritten as 2x all squared dx. And notice I still don't quite have the form that I need. I need a real number squared. I need a positive real number squared plus a variable squared, and here I have 2 times a variable squared, so I don't quite have the form that I want to apply the formula directly. So what we can do is make a u substitution. So I can let u equal to 2x. So u equal to 2x, and if I do that, then du dx, the derivative of both sides with respect to x, will equal 2. And by algebra then, 1/2 du will equal dx, and we'll use this. So here's what dx equals, and here's what our a equals. I'm going to go one more step and rewrite things again. So I'm going to get 3/2 times, I'm going to put my integral down, I have 1 over the square root of 5 squared plus, by my u substitution, instead of 2x squared, I'll have u squared. And then we'll replace the dx with 1/2 a du. So I'm going to factor that 1/2 out in front of the integral. And now I'm in a form to which I can directly apply the antiderivative formula. So I get 3 times 1 over 2 times 2 is 3/4 times the antiderivative of 1 over a squared plus u squared is going to have 1 over a. So I'm going to get times 1 over a, but a is the square root of 5 in this problem. And then we're going to be times the arctan, or inverse tangent of, and it's going to be u over a. So I'm going to get u over a, but a is the square root of 5. And then I'm going to have plus my constant of integration. And because I made a u sub, I'm going to replace the u with the 2x from the substitution. So I'm going to get 3 times 1 is 3 over 4 times the square root of 5 times the arctan of u, but u is equal to 2x over the square root of 5 plus the constant of integration. And this is good to go right here. You could rationalize the denominator if you wanted to. I don't think it's necessary, but if you wanted to rationalize the denominator, you certainly could. So we could multiply this by root 5 over root 5 if we wanted to. Arctan of 2x over the square root of 5, and we can multiply this by root 5 over root 5 plus that constant, and if we did that, we would get 3 square root of 5, and we'd have 4 times 5 is a 20 in the denominator. Arctan of 2 root 5x in the numerator over 5 in the denominator. Again, I don't think there's any reason why we have to do that, but we certainly could if we wanted to.